Okay, so chemical equilibrium, or equilibrium in general, is what we're going to be talking about today, and an expression that helps us quantify values for products and reactants at equilibrium called Keq is where we're headed. Okay? Any case, before we get to that, the basics of equilibrium was shown through a demonstration today I did with water tanks. And I set up a tank with a lot of water and a tank with a little bit of water, and I set up one person, okay, with a large cup, and that was usually me, and then I had someone with a smaller cup. And what I asked the group was, when do we achieve equilibrium? Now, in the word equilibrium, people realize there's something that's equal. And I did not give that away. I let that happen. So when we reach chemical equilibrium, the reactants become products, and the products become reactants, and you'll notice something called a double arrow, okay, showing that products can become reactants and reactants are products. Now, a double arrow usually defines that an equilibrium is occurring or can be occurred, okay, but it just means that the products can decompose into reactants and reactants can become products. So both reactions are possible back and forth. So in a reversible system like this is, I had the large cup, and clearly what happened is I was scooping up a lot more water than my counterpart. So clearly by scooping up more water and pouring it into here, this level was rising and this was decreasing because the person with the smaller cup couldn't counteract my larger volume that I was pouring. So the smaller cup person was pouring only a little bit, but I was taking a lot more initially. So therefore, again, my tank was decreasing and this tank was increasing. Some people, incorrectly, but it's totally understandable, thought equilibrium when these both, okay, when this rose to this line and when this decreased to this line, when both tanks had the same amount, people thought that was equilibrium. But equilibrium is nothing to do, or has nothing to do, with the amount of products and reactants, only about what happens to them at equilibrium. So equilibrium is not about how much of the products and reactants. It's about something else. So as we continued, of course, this line dropped even further, and this line went even higher. But it didn't keep going. Eventually, we achieved a new top of the tank of water, and this one got lower. And what happened here was that my big cup eventually couldn't scoop up that much water in the bottom, and this little cup was actually taking full scoops. So what happens over time, and it didn't take too long, because initially the reactants became products faster. That's why they went down, and products were reforming reactants. I'll say that again. Initially, because of the bigger cup, reactants were going faster, or the reactants were producing products faster than the products reforming the reactants. That's why there was a change. But eventually, we got to a point where the levels didn't change anymore because I was only scooping up my cup a little bit. I couldn't get full scoops anymore as the level got lower, and the person who had the small cup was getting full scoops. And the demonstration was done was when I took my scoop and my cup and I poured it and I filled almost completely the little cup. So only when we were pouring the same amount of water, and I was limited because of the little amount of water, my big cup couldn't scoop up as much anymore. So when I could only pour, okay, the same amount of water this way as this person poured this way, that is when equilibrium was established. So what is equal at equilibrium? The rate of the forward reaction is equal to the rate of the reverse reaction. So it's not about how much, it's about how fast each forward and reverse process was. And when those rates were equal, we're at equilibrium. And something special happens at equilibrium. At equilibrium, because the rates are equal, the amounts, and this is very important, the amount of each reactant and product stay the same or stay constant. It looks like nothing goes on in equilibrium. These levels will stay this way forever because I'm pouring the same amount of water into this tank as this person is pouring into this tank. And these levels will stay that way. And it looks boring, it looks like nothing is going on, but we do know water is still being exchanged. That's why sometimes we'll hear the word dynamic equilibrium. Dynamic means motion. It looks like nothing is going on because the rates of the forward and reverse are the same, but we know there's switching sides. And the analogy I love to use is if I have 10 people on this side and I have 2 people on this side, and we switch places one person at a time, so for every 1 minute, one person on this slide goes to this side, and one person to this side goes to this side, we can come back many minutes later, and there's still always going to be 10 people on this side, and still 2 people. It looks that these numbers, guess what? Stay constant. And they do so because the rates of people going over here equal the rates of people going over here. The people are changing sides. There is something going on. That's why they call it dynamic, but the amount stays constant. Okay? And that is what equilibrium is. Now, we have chemical equilibrium and we have physical equilibrium. So let's go over some basics here so you can understand which one is different. Now, we have phase equilibrium. Now, phase equilibrium, if you haven't already guessed, is when you have changes of phase. H2O, solid, is in equilibrium with H2O, liquid. Okay, where does that occur? Well, on a heating curve that we did earlier in the year, this was the solid. This was the liquid. And this is the solid becoming a liquid. And this is the place where we had the phase change. And this is where both were available, or we'd sometimes say both are at equilibrium at this position. And this equilibrium position is 0 degrees Celsius. Now, if we kept adding heat, we would drive the reaction, okay, to the liquid because it's an endothermic process, and adding heat would drive it forward. We'll learn about Le Chatelier's principle later. But if you stay at 0, both can occur, which means if I have a cooler full of ice, that's my igloo cooler, and I was to have a nice square block, 1 kilogram block of ice, okay, it floats, less dense, and it was the perfect cooler so that no heat, this is heat trying to get in, but it can't, okay, so heat can't get into the cool party, okay, now, so it stays out, and of course, what actually happens is you have some melting and you have some refreezing. So over time, the shape of this 1 kilogram block changes, but the mass stays constant. Now, in real life, it's hard to keep the heat out, so the heat eventually trickles in, and the rate of melting is a little bit faster, and it does decrease. But in a perfect cooler, the rate of melting and the rate of refreezing would occur. In fact, we've had some movies that I played for you in colligative properties, and I think I'll play one now. So here we have some ice and we have some free liquid at 0 degrees Celsius, and here is the phase equilibrium that would occur, that refreezing and that melting.
When water freezes, its molecules leave the liquid phase and attach to other molecules in the solid phase. At the freezing point, an equal number of molecules move into and out of the solid phase.
So you see some melting and some refreezing, and that's why the mass would stay constant, okay, in a perfect cooler. Now we also, if we continue this line upward here, we have liquid going to gas, okay? So here we have another phase change, and that would be H2O liquid, evaporation, going to H2O gas. But we can also have the reverse happen. at this temperature if we're stuck at 100 degrees Celsius. So if you keep it at 100, both things can occur, okay? However, we don't have to be at 100 degrees Celsius for both of these to occur. We can be at much lower temperatures, okay? Case in point, okay, if you've got a bottle of water, as I talked about in class probably. This is a really cool bottle of water. Okay, if you bring this kind of bottle of water, you'll probably be in trouble. Okay, any case, so we have a level of liquid here, water, and we have evaporation into the gas phase, and then we have some gases condensing. And you know that this must be occurring at equilibrium, even though it's not at 100, because this level doesn't change. The amount of H2O liquid stays constant. So therefore, we're at equilibrium. Okay, and you know that to be true, so let's play another movie of phase equilibrium. Okay, so you'll notice that there'll be molecules that'll evaporate and some that condense with the top stoppered. And this is, again, phase equilibrium.
The vapor pressure of a liquid depends on the ability of the liquid's molecules to break intermolecular forces and escape into the vapor phase. A molecule can escape only when it has enough.
All right, you get the point. Okay, enough of that guy. All right, so that's phase equilibrium. Okay, and now we have something called solution equilibrium. Now, solution equilibrium is when you have something dissolved. Now, it's very important you understand this. If I have some solid, okay, undissolved in the bottom, that means that, let's say I have lead iodide, why not? And it breaks apart to lead plus 2 ions and 2 iodine ions. Okay, these are aqueous, and this is a solid. Well, guess what? The solid dissolves as fast as the ions reform. So we have some dissolving, but we also have some recrystallization or reprecipitation. So this changes shape kind of like the ice, okay, melting and refreezing, except this is going to be called dissolving and precipitation. But this only works when the solution is saturated. It's important you know that. Because if this wasn't saturated, okay, then the rate of dissolving would be faster than the rate of precipitation. And the analogy I give here is if I had a room that fits 100 people, and I had 2 doors, and it was stuffed with 100 people, and I took one more person, that would be me, definitely me, and I stuffed myself into this room, one person would have to come out because there's only room for 100. So as many as I stuff in, they would have to be stuffed out. Well, that's how this works. If I force one person out, okay, me again, how can you tell? That would force a molecule to back in. Okay, same idea. So this solution has to be saturated. Same thing with phase equilibrium. When you open a soda bottle, the CO2 under lower pressure comes out. Now if you cap it, the CO2 is going to keep coming into this space until it's saturated. Once it's saturated, then every time a CO2 molecule is forced out of the 100-person room, some are forced back into the liquid phase. So if you keep opening and closing a soda bottle, your soda is going to get flat fast because every time you open and close, you destroy equilibrium, and the CO2 has to saturate this. Okay? And that's something to hold. So the air has to be saturated here as well as here. Okay, in a solution. So solution equilibrium, dissolving of the solid into the aqueous ions goes as fast as this goes back here. Now, something to note about equilibrium. They're very temperature sensitive, especially chemical equilibrium. But there's your phase equilibrium, and there's a solution equilibrium. And let's go on to chemical equilibrium. Now, chemical equilibrium is nothing more than chemical reactions. Those were physical processes. Now, chemical reactions, okay, same idea. You have A plus B being formed into AB as fast as AB decomposes. Okay, and that would be equilibrium. The problem with chemical equilibrium, though, is that a lot of times we want to know who's favored at equilibrium. Case in point, let's go back to our discussion in the front here. We had these tanks. Our equilibrium was favored in the products in the tank demonstration that I drew here. At equilibrium, when these stayed constant, there was a heck of a lot more products than reactants. And chemists want to know if reactions become more favored in the products or the reactants way. Because if I'm trying to make products and I have gases as part of my reaction and they're in my container, I know at the end of the day they'll be mostly products if the products are favored. So we have to have some kind of way to evaluate when and how much, okay, products or reactants are favored once they reach equilibrium. We do so by Keq. Keq is a value that helps chemists figure out, okay, who's more favored. Now, to get a Keq value, they realize that the rate of the forward is equal to the rate of the reverse. Hey, rate law! So R is equal to K, and if this is one elementary reaction, of course it becomes first order, equals R, R a K of the reverse. I'll just put a little R for reverse. This is the forward. And guess what? AB to the first power, because they're just one of them. And so, gosh darn it, these values are equal to each other. So what they do for K equilibrium, to see who's favored, they put the rate of the forward, of the reverse, I'm sorry, over the rate of the forward. And what you get is something called law of mass action. Rate law is coming to town again, your favorite, but no big deal. So to do this basic reaction, to make an expression, what we do is we take, again, the concentrations of the products to their stoichiometric coefficients become their exponents. The reactants go on the bottom to their stoichiometric orders as well. I don't have to put the ones there. And this would equal Keq. You may say, well, what happened to the rate laws? Well, we're going to say the rate laws somewhat canceled here. Okay? It's not, if we're equal the same rate, technically speaking, these guys could go bye-bye. Okay? But that's essentially what we're doing, is we're comparing the rates of the forward over the reverse over the products. And the reason why I put the products up here is just how we've set it up. So there's a rule to do this, and it has a couple of rules. Number one, to do a law of mass action, to find the expression, it's products over reactants, so the concentration of the products. 2, coefficients become exponents because we're dealing with rate law in a single step idea. And 3, solids and liquids do not apply. And you may say, well, why not? Why can't I put solids and liquids in my expression? Well, because rate law is based on concentration, and concentrations are based on molarity. And a solid or a liquid aren't a mixture. What's the molarity of a solid? What's the molarity of a pure liquid? The only thing that has a molarity, remember, molarity is a what? Moles of solute over liter of solution. The only two things that are solutions are aqueous, and gases are considered to be solutions, right? Remember? Because sometimes you walk on the field and you get into a pocket of what? No oxygens. Remember, gases are homogeneous mixtures. They're solutions too. So, to do the law of mass action is skill. You have to be able to use this law. Now, why do we do this? Why do we find this expression? Well, once we have this expression done for a reaction, if Keq is larger than 1, then this number is bigger. If Keq is less than 1, the reactants are bigger. So what that means is if Keq is larger than 1, the reactants, if Keq is larger than 1, the products are favored at equilibrium. There's a lot more products, just like the tanks that we just did here. And of course, if Keq is less than 1, the reactants are favored at equilibrium. And we want to know this. This is something we definitely want to know as we build chemical reactions and factories and do chemical processes. We want to know if the forward reaction is favored or not. Because if it's not, boy, we have to do some more chemistry to make it happen. So let's go to our worksheet and build these KAQs. And I'll do some of them together. Okay, so taking out this worksheet, here's the reaction. I want to make the law of mass action or the equilibrium expression, which is going to tell me who's favored at equilibrium, which is based on rate law. And products over reactants, so CO2, coefficients become exponents, so it looks like CO2 to the second power, okay, so that would be CO2 is the products to the second power, that coefficient becomes the exponent, it's an elementary step, and the reactants, CO, it's a bracket to show concentration, it's a rate law, and O2. Of course, that would be choice D. That's all. Now let's do number A. Products over reactants, except right away I know something. A solid can't have a concentration, and these guys go bye-bye. So it's products over reactants. Here's my products, aluminum oxide, bracket, over reactants, products over reactants, coefficients become exponents, so that's a 1, leave it blank, same thing. This is a 3. Solids and liquids don't apply, and that's equal to KQ. All right, we'll let you do B. Okay, there you go. There's a KQ for that. Notice I didn't put out the liquids. All right. And that's what we're doing here. So I want you to do C and D. I want you to answer these questions. And I want you to also try number 1. Oops. And 2. Okay, now you notice these says KSPs. And if you notice, you'll see Kc. These are all just different names for the same thing. This is an equilibrium concentration. Same thing as Kq, it's the same thing. Ksp is for different types of reactions, for ionization reactions. So this ionization reaction, if I was to do it, notice right away, solid doesn't appear, so it's products over 1. So notice there's not going to be these guys. These guys are all what? Look at that as your answer again. There's no reactant, so it's over 1 or just by itself. And because ionization reactions always have solids in them, they're all going to look the same way. In fact, they're just going to be the product of the ion concentration. Isn't solubility the measure how many ions will dissociate? My friends in chemistry, if the solid reaches equilibrium, solution equilibrium, like we drew before when it was saturated, then you're going to have these ions dissolved. So Ks and Kq of these reactions are really a measure of solubility. When the Keq is high, there's more products. Well, who are the products? The ions. So when it is a solid breaking apart into ions, an ionization reaction, the equilibrium constant we call is a Ksp because we call it a solubility product. The value of the Keq or Ksp, if you want to call it that, is the product of these ions. And the things that are more soluble will have a higher Ksp or Keq. They're the same thing. We just call it Ksp to remind people we're dealing with solids dissolving. All right? It's a special name because it's just one type of reaction. All right? And the higher the K, whether you call it Ksp or K, the more what? Products you have. And higher products and these types of reaction means more ions. So it's a measure of solubility. So do up to number 1 and 2. Good luck. See you tomorrow. Hi, Caitlin.